Hello, and welcome to the section where we'll talk about how to split our programs into multiple processes capable of running on multiple CPU cores simultaneously. In this section, we're going to first talk about what might want to have a multiprocess program and what circumstances make it a good idea. Then we'll look at 3 different Python standard library packages that allow us to create multiple processes. First, we'll look at Concurrent Futures, a high-level interface which makes the creation and use of worker processes simple. Concurrent Futures is built on top of the multiprocessing library, which is a mid-level interface that is not so simple as Concurrent Futures, but which gives us some extra flexibility in how our processes interact. Multiprocessing, in turn, is built on top of the subprocess library, a low-level interface which technically provides us with even more flexibility, but it's obscured by the need to deal with all sorts of trivialities before we get anything significant done. Subprocess is built on even lower-level operating system-specific functionality, but we're not going to get into that in this section. Finally, we'll look at a technique to squeeze a bit more performance out of multiple process programs by addressing the interprocess communication bottleneck. Just a note, at the time I'm recording this, there's a proposal to add a new mechanism to Python which would allow us to run independent Python interpreters in multiple operating system threads. This would allow another form of concurrency in Python, semantically similar to multiple processes, but with significantly faster communication. Time will tell if this feature is accepted or not, but it's something to keep an eye on. The proposal is referred to as PEP 554 and is currently targeted at Python 3.8. Let's start the video using Concurrent Futures to launch and manage worker processes. In this video, we're going to talk about what the strengths and weaknesses of Concurrent Futures are, and when to pick it. Then we'll see how to use it to create and manage a herd of worker processes. We use multiple processes when we want to make full use of the computing power of all of the CPUs in the computer our program is running on. In other words, when our program is CPU bound. If our program spends most of its time waiting for user input, network input, etc., in other words, if our program is I/O bound, multiple processes don't give us any benefit at all. So, if we're using multiple processes, it's because we have some computationally intense job to do. The most common way to structure a program in that case is to have a controller process and a number of worker processes. The controller process dispatches work units to the workers, which perform the work and then return work results to the controller, before collecting a new work unit and repeating. A work unit just represents some part of our overall job that can be broken off and performed independently. The controller's job is to decide what the work units are, assign them to workers, and then combine the work results back into the final result of our computation. This is exactly the paradigm that Concurrent Futures supports. So if we have a job to do that can be structured in this way, Concurrent Futures is going to be the easiest way to do it efficiently. Here we have a program that calculates the factorials of the first 1,000 non-negative integers. Each of the numbers to factorialize is treated as a work unit, and the factorials of those numbers are the work results. The output of the factorial calculation grows quickly, making this a moderately reasonable example of a CPU-bound operation. We're going to use a process pool executor to make our program use multiple processes to run its computations. This is part of the Concurrent Futures package. The process pool executor's job is to wrap up the complexities of running and communicating with multiple processes inside a pretty straightforward interface. We called this function worker because that's the role it fills in our program. This is the function that will be run in our worker processes to perform computations. However, it would also have been reasonable to call it factorial, since that's what it actually does. The controller function is run in our controller process, which also happens to be our original process. The first thing the controller function does is to create an instance of the process pool executor. We'll use that object to control and communicate with our workers. It's possible to tell the process pool how many worker processes we want to use as a parameter to the constructor. However, if we omit that parameter, the process pool automatically uses the number of logical CPUs available as the number of worker processes. That's almost always the best choice, so we'll usually just let the process pool decide. The Executors Map Method is probably the simplest mechanism there is for farming out tasks to worker processes. We pass it a function to use and 0 or more lists or other finite iterables of the input data for the function, and we get back an iterator of the results. Each of the input iterables provides one parameter value for each time the function is run. So if we provide 3 parameter iterables, the first element of each iterable are the parameters for the first time the function is run. The second elements of each iterable are the parameters for the second time the function is run, and so on. If you're noticing a similarity here to the map functions we've seen before, well, you're right. The idea of a map function is a powerful one, and it's applicable to a lot of situations, including this one. This map function has a whole pool of worker processes waiting in the wings, though. If your computer has 16 logical cores, the first 16 work units are sent out to the workers allocated for those cores. And each time one of those workers finishes a work unit, the result is added to the map function's results iterator, and a new work unit is sent to that worker. This keeps going until there are no more work units left. The results that come from map are always in the same order as the input parameters, so it's easy to keep track of which inputs map to which outputs. When we're done with an executor, we should allow it a chance to cleanly end the worker processes. There's another way to do that might be more appealing, which we'll see in the next example. So here we have the output from that program. No matter what happens with the worker processes, the results will always be printed out in sorted order, because that's the order that the map function provides them in. It's not necessarily the order that they were actually completed in, though. If we want to get back results as quickly as they are produced, instead of input order, we can do that, but not with map. There's another thing we can't do with map either. We can't run different functions on different worker processes. Map assumes that we want to do the same thing to each of the work units. That's a great simplifying assumption, but only when it's true. Now we're going to see how to break the constraints that map imposes, because we either need to get work results as quickly as possible, or we need to dispatch different types of work units to our workers at the same time. Or possibly both. First off, we've imported another tool from Concurrent Futures. The AsCompleted generator function can be used to help us process each work result as it becomes available. We've added this line of code to our worker function to add up to a second of additional time to how long it takes to process each work unit. In practice, that's not something we'd normally want to do. We're doing it here so that we'll be able to see the results arriving in completion order instead of input order. I mentioned before that the executor ought to be given a chance to shut down cleanly, and that there was another way to do it. This is that way. The with statement allows a special kind of object called a context manager to run code before and after the contained block of code. It happens that a process pool executor is a context manager, and the with statement allows it to automatically perform its cleanup after the code inside the with statement ends. Not only is this nicer in terms of code layout, it's also safer, because the executor is guaranteed to be shut down, even if an exception gets raised in the contained code. We'll see more on context managers in a later section of this course. Instead of using executor.map to apply the same function to all of our work units, here we're using executor.submit to dispatch each work unit individually. Each time we call submit, we tell it which function to use and which parameter values to pass to that function, which means that even though we're actually using the same function for all of them here, we didn't have to. We're also dispatching more work units than we have worker processes. That's okay. The executor will just hold on to the extras and pass pending work units out to worker processes as they complete their previous tasks. When we call executor.submit, it returns a future object to us. This isn't the same future type that we can use in an async IO-driven program, but it does the same job and even has a similar interface. As with the features we've seen before, the future returned from an executor.submit call can be used to check whether the result is available yet, and retrieve that result once it is. In this case, we're just storing all the futures in a list for the moment. Now, we can pass that list into the AsCompleted generator function, and loop over its results to retrieve individual futures in the order that their values become available. That's the same thing as saying that we process the work results in the same order as they are completed. If our processing of the work results is fast enough, we handle each work result as soon as it becomes available. To do that, we just retrieve the future's result, and then do whatever we need to do with it. This is slower than before because we added that delay to the worker function. Watching it run with the random delay, though, means that we can see that the results are not coming out in the same order that we created the worker units. Instead, they're coming out in the order of completion, like we wanted. So that's actually pretty easy, as long as what we want to do fits into the model that Concurrent Futures provides, which is most of the time since that model is commonly used and broadly applicable. However, there are times that we need to structure in the same order as they are